Tonicity refers to the ability of a solution surrounding a cell to cause that cell to gain or lose water. It is a critical concept in biology because it influences cell volume and the integrity of cell membranes. Tonicity depends on the concentration of solutes that cannot cross the cell membrane, thereby affecting the movement of water into or out of the cell. This concept is pivotal, not just in understanding cellular health, but also in the design of medical treatments. The balance of water and solutes is essential for maintaining cell function and structure. When a cell is placed in a solution with differing tonicity, it can either swell, shrink, or maintain its size, depending on the nature of its environment. This cellular response to the environment is fundamental to the concept of tonicity. Understanding this interaction helps in the formulation of solutions used in medical settings, ensuring they are compatible with body fluids. Tonicity is classified into 3 types: hypertonic, hypotonic, and isotonic. Each type has a unique effect on cells and is used differently in medical treatments. The precise adjustment of tonicity is crucial in medical applications such as intravenous fluids and other therapeutics that require direct interaction with the body's cells and tissues. Mastering the concept of tonicity and its practical applications is essential for various fields, including medicine, molecular biology, and biochemistry. This guide will explore the different types of tonicity, illustrate their effects with examples, and discuss how isotonic solutions play a vital role in medical treatments. A hypertonic solution contains a higher concentration of solutes compared to the fluid inside a cell. This means that the solution outside the cell has more dissolved particles than the fluid inside the cell, creating a concentration gradient. When a cell is exposed to a hypertonic environment, water molecules move out of the cell to balance the solute concentrations. This process is driven by osmosis, where water moves from an area of lower solute concentration to an area of higher solute concentration. This movement occurs due to osmosis, leading to cell shrinkage or crenation in some cases. Crenation is the process where cells lose water and become shriveled, which can be observed under a microscope. Understanding hypertonic solutions is crucial for applications where reducing cell volume is necessary, such as in certain therapeutic procedures. These procedures often rely on the ability to control the movement of water in and out of cells. For example, when red blood cells are placed in a hypertonic solution, they lose water and shrink, which is visually observable under a microscope. This shrinkage can affect the cell's ability to function properly. This principle is used in laboratory settings to study the robustness of cell membranes and the mechanisms of osmoregulation. Osmoregulation is the process by which cells maintain the balance of water and solutes. The knowledge of hypertonic solutions also aids in designing preservation techniques where dehydration of cells or tissues is required. These techniques are important in various fields, including medical and biological research. In medical treatments, hypertonic solutions are often used to draw fluids from specific areas, such as in cerebral edema, where reducing fluid in the brain can relieve pressure. This application is critical in emergency and critical care settings. This usage underscores the importance of hypertonic solutions in clinical settings, highlighting their role in managing medical conditions that involve fluid imbalances. Proper management of these conditions can significantly improve patient outcomes. Moreover, understanding hypertonic solutions helps healthcare professionals in ensuring that the drugs administered intravenously do not cause harm by disrupting cellular tonicity. Maintaining the correct tonicity is essential for the safety and efficacy of intravenous treatments. This makes the study of hypertonic solutions a cornerstone in therapeutic science, especially in fields dealing with fluid management and cellular health. The ability to manipulate and understand these solutions is vital for advancing medical and scientific knowledge. Hypertonic solutions have a lower concentration of solutes compared to the fluid inside a cell. This imbalance causes water to move into the cell, leading to swelling and, in extreme cases, can result in the cell bursting, a phenomenon known as lysis. Hypertonic solutions are particularly significant in the study of cells and tissues that require hydration or in conditions where cell expansion is beneficial. For instance, a common laboratory experiment involves placing plant cells in a hypertonic solution, causing them to swell but not burst due to their strong cell walls. This turgor pressure, which results from the swelling, is crucial for maintaining plant rigidity and upright position. In medical scenarios, hypertonic solutions are used carefully to treat patients with conditions where cellular hydration is needed, such as in certain types of dehydration. The use of hypertonic solutions requires precise knowledge and control to avoid adverse effects, such as cellular lysis, which could be detrimental in clinical practices. For example, administering a hypertonic solution intravenously can lead to dangerous shifts in fluid balance, emphasizing the need for careful calculation and application of these solutions in medical treatments. Furthermore, the principles of hypertonic solutions are applied in therapeutic practices such as dialysis, where the cleaning of blood is achieved by manipulating the tonicity of the surrounding solution. This manipulation ensures that waste products move from the blood into the dialysis fluid, demonstrating the practical application of hypertonic solutions in medical technology. Isotonic solutions have the same concentration of solutes as the fluid inside the cells. This balance means that there is no net movement of water into or out of the cells, maintaining cellular integrity and function. Isotonic solutions are especially significant in medical treatments to ensure that cells are not stressed by osmotic changes, which can lead to detrimental effects on cellular health. One of the most common applications of isotonic solutions is in the administration of intravenous fluids to patients who need fluid replacement but must avoid the cellular stress caused by tonicity imbalances. For example, saline solution, which is isotonic to human blood, is frequently used in hospitals to hydrate patients without causing harm to the blood cells or surrounding tissues. In sports medicine, isotonic drinks are used to replace fluids and electrolytes lost through sweating without altering the tonicity balance of the body's cells. This application is crucial for maintaining athlete performance and preventing dehydration-related illnesses. The formulation of such drinks requires precise knowledge of electrolyte concentrations to match the body's natural fluids. Moreover, isotonic solutions are used in laboratory settings for storing and handling cells and tissues. This practice ensures that the samples remain viable and unaltered for experimentation or therapeutic use, highlighting the importance of isotonic solutions in both clinical and research settings. Isotonic solutions play a pivotal role in the field of medicine, particularly in the administration of drugs and fluids through parenteral dosage forms. These solutions ensure that the administered substances do not alter the osmolarity of blood and other body fluids, which could otherwise lead to cell damage or death. This is crucial in maintaining patient safety and treatment efficacy. Intravenous IV fluids, often isotonic, are routinely used in medical settings to manage fluid balance, deliver medications, and support surgical procedures. For example, isotonic saline or dextrose solutions are common choices for IV administration because they match the osmolarity of the body's fluids, preventing the cells from undergoing osmotic stress. Isotonic solutions are also essential in pharmacological preparations to ensure that medications are delivered at the correct tonicity. This is particularly important for drugs that are administered in sensitive areas, such as the eyes or spinal cord. For instance, isotonic eye drops provide relief without causing irritation or drawing fluids out of eye tissues, which could exacerbate conditions. Moreover, isotonic solutions are instrumental in emergent medical situations, such as blood transfusions, where the replacement fluid must not disrupt the recipient's osmotic balance. This careful management of fluid tonicity helps prevent complications such as hemolysis or the destruction of blood cells or shock, underlining the critical role isotonic solutions play in complex medical treatments. Adjusting the tonicity of a solution is a fundamental technique in both pharmaceutical manufacturing and medical treatment. Various methods are employed to achieve the desired tonicity, including the addition of salts, sugars, or other solutes. Understanding these methods is crucial for professionals in healthcare and scientific research to ensure the safety and effectiveness of solutions used in medical and laboratory settings. One common method to adjust tonicity is the addition of sodium chloride or NaCl to a solution. This method is frequently used because NaCl is physiologically compatible with the body and does not generally interfere with biological functions. Adjusting the concentration of NaCl allows for precise control of the osmotic pressure of solutions used in medical treatments. Another method involves using dextrose, a type of sugar, to adjust tonicity. Dextrose is particularly useful in situations where additional energy supply is beneficial, such as in intravenous nutrition solutions. The dual role of dextrose as both a nutrient and a tonicity-adjusting agent makes it valuable in medical formulations. Additionally, the use of glycerol and other polyols can be employed to adjust the tonicity of solutions intended for particular uses, such as in ophthalmic or dermatological preparations. These substances are chosen based on their compatibility with the body and their minimal impact on cellular functions. To ensure the correct tonicity of a solution, precise calculations are necessary. These calculations involve determining the number of milliosmoles per liter, or mosmel, of the solution, which must be balanced with the osmolarity of the body's fluids. Here are some practical examples of how these calculations are performed. Consider a scenario where you need to prepare 1 liter of an isotonic saline solution, which is approximately 300 mol/ml. If pure water starts at 0 mol/ml, adding 9 grams of NaCl, which contributes about 308 mol/ml, will result in a nearly isotonic solution. This simple calculation is essential for preparing basic IV fluids in clinical settings. For a more complex example, if a medication needs to be added to an IV solution, the osmolarity contribution of the medication must be considered. Suppose a medication adds 10 mosml to the solution. To maintain isotonicity, the amount of NaCl might need to be adjusted slightly downward to counterbalance the added osmolarity. In another case, if preparing a hypertonic solution for a specific medical treatment, you might aim for 250 ml. This would involve using less NaCl, specifically about 7.5 grams per liter of water. These calculations ensure that the solutions administered to patients are safe and effective, preventing cellular damage due to improper osmotic conditions. To illustrate the practical application of tonicity adjustments in a real-world scenario, consider the case of a hospital that faced an outbreak of dehydration among patients during a particularly hot summer. The medical staff needed to quickly prepare large volumes of isotonic IV fluids to treat the affected patients efficiently. The pharmacy calculated the required amounts of sodium chloride and water to prepare several liters of isotonic saline solution, ensuring that each batch matched the osmolarity of the body's fluids. The prepared IV fluids helped hydrate the patients effectively without causing adverse osmotic effects, demonstrating the critical role of proper tonicity in medical treatments. Furthermore, the hospital also used isotonic solutions in the treatment of patients with burns. These solutions were used not only for hydration, but also for cleaning and treating the affected areas, ensuring that the added fluids did not exacerbate the patient's conditions by causing cellular stress or damage. This case study underscores the importance of mastering tonicity in healthcare settings, where the ability to quickly and accurately adjust the tonicity of solutions can be the difference between effective treatment and potential complications. The knowledge and skills applied in these situations are vital for ensuring patient safety and recovery. Understanding and mastering tonicity is crucial in various biological and medical contexts. From providing basic cellular health to supporting complex medical treatments, the careful adjustment of solution tonicity impacts numerous aspects of healthcare and scientific research. The ability to manipulate tonicity ensures that medical and laboratory practices are safe, effective, and tailored to meet specific needs. The examples and methods discussed in this guide provide a foundation for professionals and students in the field to develop a deep understanding of how tonicity affects biological systems and how to control it in practical scenarios. Whether it is in designing isotonic sports drinks, formulating intravenous fluids, or preparing tissues for medical procedures, the principles of tonicity are extensively applied. Moreover, the ongoing developments in medical science often require innovative applications of these principles. As new therapies and technologies emerge, the understanding of tonicity will continue to play a vital role in ensuring their success and safety. Thus, the mastery of tonicity not only enhances current medical and biological practices, but also paves the way for future advancements in health and science.